All right, so this is part 2 of our video. So we're going to share this hopefully, and I won't press the wrong button this time. Okay, so as we look here, okay, all right, so this is, in fact, let me label this here. This is the distribution of the sample mean. Okay, and you can see that that's still a little bit skewed, but it's actually much closer to normally distributed than our previous one, right? Okay. Now, the question I have, it was really cool. The population mean was exactly the same as our sample mean. Okay. That's an example of the central limit theorem. Okay. Now, let's talk a little bit about the standard deviation. Okay. Now, if I were to, how would I find the standard deviation of the population really easily, quickly and easily? STDEV, and then which one do I pick? Which one? No, we're going to do the dot P for the population, right? We're doing the population. Okay, so this is the population standard deviation, and I'm going to do this. Okay, now remember when I did this originally, I wanted my standard deviation to be about 15. Let's see how close I got with my simulation. 14.1, pretty good, right? Okay.
Just kidding.
All right, so now my question is, what if I did the standard deviation of my means? Now these are samples, right? So which one am I going to use this time? Sample, right? Now I'm going to do the standard deviation of all of these here. Now the question I have before I press enter, do you think my standard deviation will be the same as my population, or will it be different? Who thinks it will be the same? 1, 2, 3, 4, 5, 6. Who thinks it will be different? 1, 2, 3, 4. Okay? So 6 to 4. Who didn't raise your hand? Okay, you got it wrong. Okay, so here we go. Drum roll, please. It's very different. Minority one on that one. Okay? Now, there is a relationship between these two standard deviations. Okay? And the relationship is, if I take population standard deviation, and if I divide it by the square root of my sample size, now how many were in each row? 9. So I'm going to use 9 as my sample size. What this will do is it will give me a really good estimate of the standard deviation. So I got 4.83, and now I got 4.71. Do you see how that's pretty close? Okay. And so I think previously I told you, if I stop sharing here, previously I told you there were two formulas for the z-score, right? Do you remember those two formulas I told you? Z equals x minus mu divided by sigma.
There we go. Sigma.
Okay. That was one formula, and then the other one I gave you was z equals, it was x bar this time, minus mu over sigma
minus 1
over the square of that, right? And I told you previously that the n was always going to be 1, and that these two formulas were basically the same. Okay, now notice this time n is not going to be 1, and I'm using x bar rather than x. Okay, so these represent the central, this one here represents the central limit theorem. Okay, And so in this chapter, your n will not always be 1 this time. Okay? And we're going to be dealing with sample means and population means. And so that's why I said at the beginning of class, it's going to be critical from now through the rest of the semester that you're going to properly identify, is this a sample mean or is it a population mean? Is it a sample standard deviation or a population standard deviation? Okay? That skill is going to be crucial to your success in the rest of this class. Okay? And so what I was trying to do there is, when I just illustrated here, this is why we divide by the square root of n, because we're making an estimate. Because the idea with the central limit theorem is your standard deviation will always be smaller than your population standard deviation. Okay? And I kind of illustrated it here. Remember, we had an underlying distribution that was uniform distribution. You can see there's a lot more variation than there was in the bell curve that I drew. Okay? Because the bell curve that I drew represents the sample mean, whereas the green represents the population. Okay? But the relationship is that if I take the population standard deviation and divide it by the square root of n, I should be very close. Okay? This is what they call an unbiased estimator. So the nice thing is X bar is an unbiased estimator of mu. Okay, which is nice because we just showed you it doesn't matter whether I do the population standard, the population mean or the sample mean. The mean of the sample means is exactly the same as the mean of the population. Okay, it's unbiased. Whereas sigma over the square root of n is an unbiased estimator of the standard deviation of the sampling distribution. And so that's why we divide by the square root of n. Thanks to the central limit theorem.
Is that a square root of 1 on top of that? Or what is that?
Square root of n. This is a sigma.
Oh, sigma. Could you post this Excel thing online so that we can have it?
Sure.
And we know how to do it on Excel?
Well, yeah, you should, well, yeah. I've gotten rid of all the formulas, most of the formulas, but yeah.
Okay.
Remember, because I copy and pasted them. But yeah, but this is always a fun little demonstration that illustrates the central limit theorem. Okay? Now, the fact of the matter is, I just did a demonstration on, remember this is a continuous distribution, continuous distribution. Okay? Now, it also works with discrete distributions also work if NPQ is greater than or equal to 10. Okay? So let's do an example of that. Okay? So, let me go back here. We're going to share again. We're not going to stop the recording this time. Okay. This is a uniform distribution. This is a proportional distribution. Okay. All right, so here's what I want to do. Let's say that I want to do this for a small sample first, just to show you that it doesn't work as well. Okay? Or should I do it on a big one? What do you guys want me to do? Small one won't work, the big one will work.
One big. Go big or go home.
Okay, so let's say that I have n equals, let's say 100. And I have p equals, say, 0.3. Okay? Now, according to this interlimit q, so therefore q, if p equals 0.3, what does q equal? Equals 1 minus 0.3, which is 0.7. Okay? Now, is this big enough? Okay, how do you know the answer to that question?
Because n is greater than 30.
Oh, he said n is greater than 30, and that's the wrong answer because this is proportional data. You did the continuous data.
We need the NPQ to be greater than.
We need NPQ to be greater than or equal to 10. Okay? Maybe I'll put a question mark on there.
For NPQ, you're supposed to.
So I'm going to take n times p times q, which is going to be 21. Is that greater than 10?
Yes.
Okay, so yes, it is large enough. Okay? All right, so now, because I know you guys are to write out the sample space, okay, let's say that, this is a silly example, 30% of people pass math 1040. Okay? Now, out of 100 people, what are all the possibilities for the number of people who could pass the class?
Number of possibilities.
Mm-hmm.
Out of 100
Out of 100 people,
people, 30 would potentially pass.
well, you're giving me the expected value.
Yeah.
Okay, I want to know all the possibilities. One person could pass, right? What's another possibility? One or two or three or four. What did you forget already? Zero. Don't forget the zero. Okay. On up through, how many possibilities are there? Actually 101 because there's 0 to 100, which is 101, right? Because you forgot the zero again. Okay, so I'm going to scroll down to 101. Okay. All right, so now,
Oh.
okay, here's what I'm going to do. I'm not going to expect you to know this formula. I'm just going to fill it in because you don't need to know this. Okay, so given the idea here that 30% of the people are going to pass the class, the probability that I had 0 people pass the class is 3 times 10 to the minus 16th. That's ridiculously small. That's 15 zeros and then a 3. Okay? So it would be extremely unlikely that 0 people would pass the class given that there's 30% going to pass the class. Does that make sense? Okay? I'm going to copy this formula down, which you don't need to know, but I'm just going to copy that down just so that we can look at something, okay? Now, as we look at this, okay, now remember, the way we're measuring this is either you're going to pass or you're not going to pass, right? You've got 2 options, okay? So this is going to look, I'm going to create a histogram out of this. Hopefully, we're going to find out if this is going to work. I really don't like to use, I was afraid of that. Here, I need to fix something. Here's what I'm going to do. I'm going to do it my way because I can't trust Excel to do this right. Insert bar graph. Oh, look at that. Okay? Now, think about this for a minute. All we're doing is we're using a bunch of yes/no data. Are they going to pass or are they not going to pass? Okay? What I told you was if your sample size is large enough, this will look like a bell curve. Does that look like a bell curve to you?
Yeah.
It sure does. Isn't that cool? Okay? And so this is an illustration, once again, that even though all I'm doing is asking them, do you pass or did you not pass? If you repeat this a bunch of times, you're going to get a bell curve. Okay? So whether you're using proportional data, the proportional data, how large does your sample have to be again? NPQ greater than or equal to 10. Now, just to show you that it's not so great if your sample size is too small, I'm going to do this exact same thing but I'm going to change my sample size to 10. Okay? Everything else is going to be the same. Now I'm going to insert bar charts. Well, that actually looks better than I thought it would, but what do you think about that? Does that look like a bell curve to you? Not really. Is it big enough? According to this, now, oh, actually, it's only 2.1, right? So you can see if my sample size is 10 as opposed to 100, would you say this is right skewed or left skewed?
Right skewed.
Probably right skewed, right? Okay. All right, so once again, if your sample size is large enough, it will look like a nice bell curve. Okay? So this is an illustration of the central limit theorem. Okay? Now, I've already taught you this formula here. I'm going to teach you another z-score formula. Okay? This other z-score formula is going to work when you're dealing with proportional data. Okay? So it's going to be z equals p hat minus p over the square root of pq divided by n.
What is that?
Okay? This is the z-score that we're going to use when we're using proportional data. This is the z-score we're going to use when we're using means or continuous data. Okay? So I've got two z-score formulas. So the idea here is if you're using a mean, you're going to use this formula. And if you're using a proportion, you're going to use this formula. Okay? PQ, yes. Okay? Was there a question?
No, I just wanted to know if that was PQ.
Yeah, PQ. Okay. So here's what I would like to do. I'd like to do I'm going to illustrate a couple of examples. Okay? Now this would be very similar to our when we did the normal distribution previously. So let's say, for example, if I can find an eraser here. That the mean weight gain during pregnancy is 30 pounds. Weight gain is skewed right. Okay, when I say skewed right, how would I draw, if I were to draw a picture, what would that look like? Yeah, so it's going to look something like this, right? Okay. With a standard deviation of 12.9 pounds. An obstetrician in a low income neighborhood obtains simple random sample of 35 women and finds the mean weight gain was 36.2 pounds. Should she be concerned? Okay, and actually, is it unusual if a woman gains 36.2 pounds? Okay, so here's what I want to do. I want to do this both ways. Even though this is not normally distributed, we're going to assume we're going to do this for one woman, and then we're going to do it for her 35 women. Okay, I want to see what the difference is. Okay, so if we were to do this for one woman, so that one woman gains 36.2 pounds, Brenda, how would we, let's, oh, I guess I should define what would be unusual. Okay, is it unusual? Okay, we're going to define unusual as happens less than 5% of the time. Okay, that'll be our rule. Okay, so if it happens less than 5% of the time, we're going to say that that's unusual. Okay, that'll be our definition of unusual. Okay, so Brenda, how would I figure out if it was unusual if a single woman gained 36.2 pounds during pregnancy? I want you to use this equation here. Okay. So you don't remember this equation before?
Yeah.
So what do you think X would represent in this equation? What did you say?
One woman,
The one woman, and how much did she gain? 36.2 pounds. Okay. Minus the mean. And we're making a bad assumption that this is normally distributed, but we're just doing it just anyway. Okay, we probably shouldn't do this because it's skewed, but we're going to do it anyway. Okay. What's the mean weight that a woman gains? 30 pounds. Divided by 12.9 and divided by the square root of how many women are we dealing with this time?
5.
A woman, which would be 1. Okay? All right, so this gives me 6.2 divided by 12.9, and that equals what? That equals 0.48. Okay, now what did I just do when I used this equation here? First of all, I'm going to change my curve. We assumed that it was normally distributed, right? Which is probably a bad assumption, but I'm just doing this for illustration purposes. If we assume that this is normally distributed, which it's not, but let's assume it is for just a moment, okay? What is the mean of a standard normal distribution? Zero, right? Okay. Now, normally a woman, well, here, I'm going to draw it here. This is really what we're talking about. She's gained 36.2 pounds, right? She's on the right side here. Okay. I'm going to pretend that it's normally distributed. Okay. So she's gaining 36.2 pounds. Okay. With this equation here, I've just converted this to, rather than a mean of 30, the mean is now 0. And I got a value of 0.48. What does that represent?
Standard deviations.
It's the standard deviation. So I am now 0.48 standard deviations to the right. Okay. So what percent of women gain more than 36.2 pounds. How would you figure that out?
For one standard deviation.
Can't hear you.
One standard deviation, okay, it's just 60.
Well, 68% would be between one standard deviation, right? How do you figure out what's in this tail? We're going to have to do, well, 1 minus, but the problem is 68% cuts off the tail, right? Okay, have I showed you how to use the chart yet?
Yeah.
I thought I did. Okay, so I'm going to give you guys, let me start sharing the screen here. Okay. Now I've posted the chart up on, in fact, let's make sure it's still on the website. If I go to course, if I go to announcements, and I've got the formula sheets, the very first announcement posted to Clearback on January 8th. Okay, you may want to, you probably want to print this out. Okay, so I've got this Excel sheet that I'm going to give to you, this Excel sheet, so I'm on the normal distribution. Okay. Now notice I've got this picture here, and it tells you what is shaded to the left, but in my case, I want what's shaded to the right. Well, yeah, it should be the same. You could think of it that way, but here's the idea. So I'm looking at 0.48 on my value here, okay? So 0.48, okay? What this actually tells me here is 68 point, oh, that you kept saying 68%, but we're not using the 68, 95, 99 rule. What this is telling me is I've got 0.6844 to the left of 36.2 pounds. If I've got 0.6844 to the left, what do I have to the right?
You'll have 31.56.
Equals 1 minus, oh, sorry, I can't enable. Okay, so I'm at 0.48. This is the number I've got here. I'm going to highlight it so we can see it. Okay. I've got 1 minus that number to the right. Does that make sense? So 31.56. So it's 0.3156. Leave all of your answers as a decimal there. So the idea here is 31.5% of women gain more weight than she does. Is it unusual for a woman to gain 36 pounds?
Yes.
It's not unusual, because that's greater than 5%. Okay. Now I want to do the same thing, and this time we're going to do 35 women. Would it be unusual for 35 women to gain 36 pounds? What do you guys think?
I feel like it depends on the size of the population.
It depends on the size of the sample. Population doesn't matter. Because according to the law of large numbers, if our sample size is large enough, it's going to reflect the population. Okay? So we know that the mean is 30 pounds. She's getting a mean of 36 pounds in her neighborhood. Are the women in her neighborhood gaining more weight than the average women?
Yeah.
That's the question we're trying to ask. Okay? So we're going to do this exact same example again. Okay? But this time, rather than 1 woman, we're going to change this to 35 women. Okay? That's the only thing we've done is we've changed that. Okay? When we plug it into our equation here, and I know we're out of time, so I'm going to hustle on here. Okay? Divided by square root of 35, okay, we get 2.84, okay? So now the idea here is, okay, rather than being 0.48 standard deviations, we are now 2.84 standard deviations away. That's a lot more standard deviations away, right? So we're now 2.84. What's the area of this when you're 2.84 standard deviations away? How do you figure that out?
I'll use that chart.
We're going to use that chart again, okay? So your homework is going to be using this chart, okay? We're now 2.84 standard deviations away. 2.84 is 0.9977, okay? What if this is now 0.9977, what is this value here?
2.0023.
1 minus that number there. 0.0023. Value now is 0.0023. Is that unusual? Okay, so here's the idea. A single woman, 36 pounds, probably not a big deal, but if you've got a whole neighborhood of women that are gaining a lot of weight, that means they're different than the rest of the women. The question is, why is that? Why are these women gaining more weight than the others? Okay? Now, the same thing works. I wish we could have done an example with this one here, but your homework is going to be either using either one of these two equations here, and you'll just have to say, about if I'm using a proportion, I'm going to use this equation. If I'm using a mean, I'm going to use this equation. Okay? So quiz on Tuesday will be on chapter 12 and the central limit theorem. Chapter 15, thank you. And we'll see you all on Tuesday.
Can you post that example on Canvas so then I can go over
Sure.
it on Excel? Thank you so much.
Release, I was wondering if I could hurry and take the quiz, if that's okay, or
Didn't you walk in when I put all the answers up?
I don't
Here, let me
remember
turn
them.
off this recording. We're recording all this.